Question number 21. Which one of the following statements is correct with regard to elements from scandium to zinc in the periodic table and their compounds? Statement number 1. They have lower densities than potassium and calcium. As you can see here, potassium, calcium, and all the elements from scandium to zinc are in the fourth period of the periodic table. But potassium and calcium belong to the S block, whereas scandium to zinc are elements of the D block. So we know that D block elements have a higher density than S block elements in the same period. Therefore, the first statement is false. Second statement. Some of them exhibit non-metallic properties. That is false. D block consists of metals. Statement number 3. Aqueous dichromate is converted to aqueous chromate and chromium 3+ ion upon addition of dilute sodium hydroxide. Dilute sodium hydroxide is a basic medium. Therefore, dichromate does not all the way advance to chromium 3+ ion, but it stops at chromate, aqueous ion. Therefore, this statement is false. Here is the redox reaction related to that statement. Dichromate goes to chromate in basic medium. Statement number 4. They have electronegativities lower than S block elements in the same period. Electronegativity is the ability of an atom to attract the bond electrons towards itself. According to this graph, along the period, the electronegativity value increases up to copper, and there's a slight decrease in zinc due to its somewhat saturated nature. Therefore, statement 4 is false. Statement 5. Manganese forms acidic, amphoteric, and basic oxides. That statement is true. Here are some examples. Question number 22. The standard enthalpies of combustion of solid carbon, solid sulfur, and liquid carbon disulfide are -394, -296, and -1072 respectively. The standard enthalpy of formation of liquid carbon disulfide is. So we basically move on to Hess law. So this is the diagram for this question. We have to calculate this value. So this is a calculation. You have enthalpy of formation on this side, and then the enthalpy from carbon disulfide to sulfur dioxide and carbon dioxide, and the other side where solid carbon and solid sulfur moves on to sulfur dioxide and carbon dioxide. The answer is positive 86 kilojoules per mole. So that is answer number 2. If we have an easier way to do this without writing down the calculation, it will be this. So we have 394, which can be rounded up to 400, and then 296, which can be rounded up to 300. 300 into 2 is 600, and 400 are 1000. So this side of the reaction is 1000, -1000. And this side we have the enthalpy of formation, and then -1072. In the calculation, -1072 moves on to the other side, making it +1072. And when you simplify that, you get +72. If you look at the answers, there is no +72, but what is the closest answer to 72? It's 86. So we have the answer number 2 again, +86. Question number 23. Which of the following arrangements gives the correct increasing order of the reactivities of the above compounds towards HBr? So as we can see, we have alkenes and this kind of reaction is an electrophilic addition reaction. So in these kind of reactions, the reactivity depends on the intermediate carbocation and the stability of it. When we take the reaction itself, this is how it happens, the electrophilic addition reaction. And the stability of the carbocation depends on the positive charge on the carbon. If the positive charge is less, the stability is high, and vice versa. The CH3 groups push the electrons away from themselves, reducing the positivity on the carbon. So greater the number of CH3 groups attached to the positive carbon, the greater the stability of the carbocation. So a primary carbocation has one CH3 group, then secondary has 2, and tertiary has 3. Therefore, the stability increases in the same order. Now we move on to our A molecule. It has 2 R groups attached to it. Therefore, it's a secondary carbocation. When we go to B, it is a primary carbocation because it only has 1 R group attached to it. Molecule C has 1 R group and a carboxyl group attached to it. We know that the carboxyl group attracts electrons towards themselves because of the oxygen. Therefore, the positivity on the C increases. Then molecule D is a tertiary carbocation because it has 3 R groups attached to it. Now we'll arrange them in order. C should be the least reactive because it has the highest positivity on the carbocation because of the carboxyl group attached to it. Therefore, we can eliminate answer number 1, 2 and 5. So that leaves us with 3 and 4. When we look at A, B and D, B is a primary carbocation. Therefore, B should be the second one in line. That gives us answer number 3. But if we move on to the other two, A is a secondary carbocation, so that should come after B, and then D, the most stable, which is a tertiary carbocation. So the answer is answer number 3. Question number 24. Ammoniacal copper chloride can be used to distinguish between alkyne and an alkene because... Before we move on to the statements, let's look at the 2 molecules that are given to us, the alkene and the alkyne. The carbon atoms forming the alkene bond or the double bond are in the sp2 hybridization state, whereas the carbon atoms forming the triple bond are in the sp state. We know that the sp2 has 33% S character, whereas sp has 50% S character, which means the bond electrons in the alkyne carbon are closer to the protons than the bond electrons in the alkene carbon, placing the bond electrons in the alkyne in a lower energy state, which in turn makes the anion a more stable anion than the anion made by the alkene. This gives a slight polarization to the CH bond in the alkyne, making it easier for the H to be released. When we add copper chloride, what happens is the positive copper ion goes and displaces the H of the alkyne, forming the alkyne anion, which is a very strong base. This copper compound precipitates as a red precipitate. Also, please note that the carbon-copper bond is not a covalent bond, but is an ionic bond. Now let's look at the first statement. The alkyne is oxidized by copper chloride faster than the alkene. This is not a redox reaction. So in the beginning, in an alkyne state, the carbon has the oxidation number of 4, and also in the ion, it has the number 4. Therefore, we can safely eliminate statement number 1 as well as 2, which says alkyne is reduced by copper chloride faster than alkene. The third statement states The alkyne can oxidize the copper 1 plus ion into copper 2 plus ion, while the alkene cannot. Again, this is not a redox reaction, so we can eliminate the statement number 3 also. Now let's move on to statement number 5. The alkyne undergoes an electrophilic addition reaction with copper chloride, while alkene does not. This is not an addition reaction, it is rather a substitution. So we can eliminate statement number 5 too. Now let's take a look at the correct answer, which is statement number 4. The alkyne contains an acidic hydrogen which can be displaced by copper 1 plus ion, while the alkene does not. That is true. Question number 25. An aqueous saturated solution of MOH2 has a pH of 10 at 25 degrees Celsius. The solubility product of MOH2 at the same temperature is. Solubility is calculated through KSP. For KSP, we need the concentrations of M as well as OH. They've given us pH, so through that we can find POH. pH plus POH is 14, and when we calculate that, POH is 4. Using POH, we can calculate the OH minus concentration, which is 10 to the power minus 4. Now let's take a look at how the MOH2 molecule dissociates. It's M2 plus 2 OH minus, giving them a 1 to 2 ratio. Therefore, the concentration of M2 plus ions should be half of the hydroxyl concentration, which gives us 5 into 10 to the power minus 5 moles per cubic decimeter. Now moving on to calculation of KSP, which is pretty easy. We get 5 into 10 to the power minus 13, which is the answer number 3. Now if we are to do this calculation without touching a pen, how would we do it? So pH is given to us as 10. Therefore, we can get POH as 4. And from there easily we can get the OH minus concentration as 10 to the power minus 4. And from the reaction, we know the ratio between M2 plus to OH minus should be 1 to 2. Therefore, the concentration of M2 plus should be half of the concentration of OH minus, which has to have a 5 in it, because we are dividing 1 by 2. And when calculating KSP, 5 does not change because 5 should be multiplied by 1. Therefore, the answer should have a number 5 in it, which only leads us to number 3 as the answer. Question number 26. The correct decreasing order of the NO bond distance in the hydroxylamine, nitrogen oxide, nitrite, and nitrate is. The NO bond length is determined by the NO bond order. That is basically the distribution of the pi bond of the NO among the rest of the bonds. If we take hydroxylamine, it only has a sigma bond between N and O, so the bond order is 1. In nitrogen oxide, there is a strong double bond, so the bond order is 2. Also, the double bond is not distributed because it only has 2 nuclei in the molecule. In nitrite ion, there is one double bond between N and O, and there is another sigma bond between N and the other O. Therefore, that double bond, when the resonance structures are drawn, is spread through the 2 bonds. Therefore, a single bond has 1 sigma bond and half of the pi bond, therefore giving us 1.5 bond order. Same goes to nitrite, but in this case there are 3 bonds which share the double bond, giving the bond order 1 sigma bond and 1/3 of a pi bond. Denser the electron cloud between 2 atoms, shorter the bond, which could be directly translated as higher the bond order, shorter the distance. According to that theory, hydroxylamine has the longest bond, which only consists of one sigma bond. Then comes nitrate with an addition of 1/3 of a pi bond. Then comes nitrite, and at last we have nitrogen oxide. So the answer is answer number 4. Question number 27. Which of the following statements is correct with regard to the chemistry of group 1 and 2 elements and their compounds? This question has been given an all. Let's see why. Statement number 1. All group 1 and 2 elements react with cold water to give H2 and their metal hydroxides. This is false, as we know beryllium does not react with water and magnesium does not react with cold water, it needs warm water. So the first statement is false. Statement number 2. Lithium nitrate decomposes on heating to give nitrogen dioxide and oxygen as gases. This one is true. Here is the reaction. Statement number 3. The solubility of group 2 sulfates decreases down the group. This is true because magnesium sulfate is a solution, whereas barium sulfate is a good precipitate. Statement number 4. The basic strength of group 2 hydroxides decreases down the group. As we go down the second group, the metallic nature of the elements increases. Therefore, the ionic bond between the metal and the hydroxide group increases in its ionic nature, making them better bases as we move down the group. Therefore, statement number 4 is false. Statement number 5. The oxides of group 2 elements can be obtained on heating their carbonates. This is true, and here is an example. So as we can see, 2, 3, and 5 statements are true. Therefore, this is an all question. Question number 28. A sample of sodium hydroxide is contaminated with an inert impurity. 4 grams of the sodium hydroxide sample was dissolved in 1 cubic decimeter of water, and a 50 cubic centimeter sample of the resulting solution was allowed to react with 50 cubic centimeters of 0.1 HCl solution. The pH of the reaction mixture was found to be 2. The percentage of purity of sodium hydroxide sample is. First of all, it is advisable to draw a little sketch out of the data given to us. Alright, now let's move on to the calculation. We are given the pH of the last solution, which is to be 2. From that, we can calculate the remaining HCl moles. From that, we can calculate the initial number of moles of HCl. And from there, the reacted moles. As we know, sodium hydroxide and HCl react 1:1 ratio. Therefore, the same amount of moles of sodium hydroxide reacted, giving us the sodium hydroxide concentration to be 0.08. For purity, we need the mass, and the mass is 3.2, and from there the purity can be calculated as 80%. That is answer 4. This question also can be done without touching a pen, but be careful, you do not want to tangle everything up. Question number 29. At room temperature, a solution of 0.1 HCl was slowly added to 100 cubic decimeters of lead nitrate solution until the reaction was complete. The resulting solution was filtered and the residue was dried to a constant mass. The mass of the dry residue was 0.139 grams. The concentration of the lead nitrate solution is. What has happened here is that all of lead in lead nitrate has precipitated as lead chloride. The lead chloride weight has been given to us. From there, we can calculate the moles. The number of lead chloride moles directly correlates with the number of Pb2 plus ions. Because of the 1:1 ratio between lead nitrate and lead chloride, the same number can be used as the lead nitrate moles. From there, we can calculate the concentration of lead nitrate to be 5 × 10 to the power minus 3 moles per cubic decimeter, which gives us number 5 as our answer. Question number 30. Which of the following compounds gives a basic gas on heating? A. Ammonium carbonate, B. Ammonium chloride, C. Ammonium nitrite, D. Ammonium nitrate, and E. Ammonium dichromate. This is an easy question. All the ammonium salts except ammonium nitrite, ammonium nitrate, and ammonium dichromate emit ammonium gas when they are heated. So we can easily come to the answer as answer number 4. Here are the reactions related to the above salts. As we can see, ammonium nitrite emits N2 gas, ammonium nitrate N2O, and ammonium dichromate forms N2 gas and chromium oxide.
Hey guys, if you liked our videos, please like, subscribe and turn on notifications. Thank you.